I would like to talk a little bit about plasma-borne green alloy making. The idea behind using plasma states for iron oxide and generally for transition metal oxide reduction lies in balancing the chemical reductant content, usually for instance green hydrogen, with electrons. And the electrons are used to bring the reductant gas, again usually hydrogen, into an excited state. And you will later see what that exactly means. And in terms of green metallurgy and green synthesis, that means that we can really bring into a balanced relationship the chemical energy and the electronic energy that could directly and with high efficiency come from renewable resources, for instance. The plasma smelting reduction has a couple of features. It would typically melt the oxide, so you reduce the metal in a liquid state, very different from direct reduction where you reduce the material in its solid state. Then you mix, of course, this ionic liquid intensely, and you can also alloy it. That means you can blend it with all kind of other things or other ores or other minerals or scrap and so on. And then you smelt it. That means you do not only melt it, but you reduce also the liquid ionic material. You can use very lean contents of hydrogen or generally of reductants like 5, 8 or 10% hydrogen are often enough to reduce an ionic liquid transition metal mixture in a plasma state. And that leads to the reduction of the material. As I said, you have a high degree of electrification because you bring electrons into the game. You can, as we will later see, clean the material, so you receive very clean metallurgical products from it. You separate things. You also have dedicated slag metallurgy, of course. You can produce multiple mixed materials, oxides and metal alloys, of course. And in part, you can exploit even reduction by evaporation, depending on the vapor pressure of the materials that you charge. So this is a basic setup in the laboratory where you can use, in principle, a standard plasma melting furnace as you use it in the laboratory to make your alloys. And in the current case, we do this by using hematite as an input oxide. And as I said, it's liquefied. The melting point of iron oxide is only slightly higher than that of the metallic iron. And then you expose it to the ignited plasma state, which is magnified here on the right-hand side. And the electrons that you are charging, depending on the current density, bring the H2, which typically has only a content of 5 to 10% in the reactor, into an excited state. That means something like H2 plus or H, even protons are possible, although the main occupation in a typical laboratory environment would be the atomic hydrogen, which makes the system much, much more reactive in terms of its reductant capacity compared to the molecular hydrogen. And then you can produce, as you see here, for instance, from hematite, pure iron within a few minutes. So it's a very, very efficient process. And here's a somewhat a bigger furnace example. I show you later even industrial furnaces, and again highlighting the point that you cannot only charge iron oxides or of course different oxides like nickel oxides, copper oxide, cobalt oxides, even manganese oxides, etc. But you can also blend it with scrap. So there are no limits to use this type of plasma furnace also as a general mixing and smelting reduction aggregate. Sometimes you hear that such big furnaces for upscaling this technology are not available in the industry, but this is incorrect, as you can see here from classical electric arc furnaces used in industry today for scrap melting. When you equip these industrial furnaces with a charging of hydrogen, you can turn them into such aggregates also at a higher scale. Of course, you would have to revisit the survival rate of these graphite electrodes or might go to different type of electrode strategies. And of course, you must revisit also the slag metallurgy and the insulation of the material. So it's not easy, but in principle, these technologies seem to be scalable. Let's look a little bit closer at the nature of the plasma in such a furnace. as we said, you can in principle in a plasma center achieve extremely high temperatures, up to several 10,000 degrees centigrade, and that when you go to the equilibrium ionization calculation using the Boltzmann calculation and the quantum mechanically calculated ionization energies, you then would arrive at a certain distribution function of hydrogen split into atomic hydrogen, so H2 split into atomic hydrogen, but even in protons and electrons and other radical species. But as you also see, the plasma is quite inhomogeneous. That means you have very hot areas, but you have at the interaction zone where the plasma hits the ionic liquid, which we try to reduce into pure metal, you have, usually 2, 3, or 4,000 degrees centigrade. And this is a highly non-equilibrium system. So due to the intense bath stirring, these temperatures often are not so well known and also very hard to measure because you rapidly form a slag on the surface of the ionic material in its liquid state. So here's an equilibrium calculation, as I had mentioned before. Here for the 10% hydrogen charging into such a plasma, the rest is balanced by argon, so we talk nearly 1 bar, so 900 millibar. And here you see, as I said, a typical equilibrium calculation that you can do in principle with a couple of Python lines, the splitting of the charged hydrogen 2 molecule into the atomic hydrogen, which, as you see in our operation conditions, is the most important reductant radical. And then upon higher temperatures, you get also released electrons and even protons as you ramp up the temperature. But again, for the typical pressures, as you see here on the right-hand side, and typical operational temperature that we use in such furnaces, you are mainly dealing, as you see from the blue curve here, with atomic hydrogen as the excited state of the H2, which then acts as a reductant. So we talk essentially atomic hydrogen. And when you want to better understand from an equilibrium standpoint how this acts as a reductant and how efficient it is, you would plot the corresponding Gibbs free energies, as you see here in a so-called Ellingham-Richardson diagram, where you balance out the free energy of the corresponding oxides and the corresponding driving force you receive from the reduction by using such radicals or other reductant gases. Here you see, of course, when you go to the bottom line, so the highest driving force, you would have, for instance, for splitting hematite Fa2 or 3 in its liquid state by protons, so at very, very high temperatures in the plasma. But also for the different excitation states, you can, in such a diagram for the equilibrium thermodynamic state, do such calculations to better understand what your required plasma state is and what the reductant potential of these species is. Here you see a OES, optical emission spectroscopy analysis, also coupled, which you cannot see in this picture, with mass spectroscopy, the analysis of the actual excited states and the evaporation states also in such a reaction chamber. And details are in the corresponding papers. Here you see a typical lab environment in this little movie that is shown here, where you see that at a lab scale these are relatively small furnaces which are comparably easy to handle and similar to setup that you already might have in your corresponding laboratory. And we do the analysis in a way that you charge the hematite is molten, and then the reduction is starting, and then we analyze the samples by interrupting the process. That means we stop the process, take samples out, look at them and analyze them in detail, as you see here, after 1 minute, 2 minutes, 5 minutes, 10 minutes, and so on, until after 30 minutes for a 10% hydrogen containing plasma state, you arrive in this case at pure metals. But already at 15 minutes you have a very high iron content. And the material, the metal that is formed during the reduction in the liquid state, has more than twice the weight of the ionic liquid, so it sinks down in the vessel very easily, so you can easily tap it and separate it from the oxide. Here's a microstructure analysis taken from the sample after 2 minutes of the 10% hydrogen containing plasma exposure. Details are here in this paper, and you can see from the microstructure analysis Here, for instance, the first droplets are formed in this yellow marker. And when you subject it to electron channeling, contrast imaging, image quality, or EBSD phase analysis, you can beautifully see that the first iron metallic content, here the ferrite, is already formed after a few minutes of plasma exposure. What you also see, very interesting, when you look closely, that the silicon, which is a typical gangue element in many ores, particularly in lower price ores, the silicon content is relatively high. You can see that the silicon in the liquid state is rejected from the iron. That means this is very important, that the silicon is rejected into the surrounding oxygen. And that means oxide. And that means that you seem to also clean the material during the reduction. And this is also rendered quantitative, as you can see here on the left-hand side. First, the temporal progress during plasma exposure and the gain in the iron, the recovery of the iron from the hematite in the plasma furnace. And you can also see the rapid decay in the metallic part of the aluminum, manganese, and silicon content, which again are the most typical gangue, that means impurity elements, of the actual iron ore that is used at the industrial scale. And also here for phosphorus and sulfur, two very important culprits that you do not want to have in steels. The same applies. That means you clean the metal very quickly from these contaminants. And the other ones, as you see here, calcium, magnesium, carbon, are very, very low in their content. And you can also quantify that as you go along during prolonged exposure to the plasma. As you can see here from an interrupted test, again, you see very nicely here the formation of the iron surrounded by the remaining wüstite. Now here, of course, in the solidified state. And you can see how the fraction of the iron recovery is growing after a process time of 1, 2, 5, 10, 30 minutes, and so on. So it's a very, very efficient and very, very fast process, as you see in these kinetic diagrams. So it's extremely quick. You can also go with the same sample here to the atomic state and prepare from these materials an atom probe tip, which is a tiny atomic scale analysis method, as you see here, to evaporate the material and look in the mass spec of the atomic scale evaporation for the cleaning effect. And again, you see when you look at the atomic scale of these quenched samples in the partially reduced state, on the right-hand side, the alpha iron, the ferrite that has already been reduced, and on the left-hand side, the remaining oxide, the wüstite. And this is shown here in the two-dimensional diagram where you see the 100% alpha iron versus the drop of the iron content in the remaining wüstite and the increase in oxygen. But particularly you can see again that the silicon that you typically do not want to have in the final iron product is indeed depleted from this gained ferrite and partitions into the remaining wüstite oxide. So it's a very, very important cleaning step, which is also here proven at the atomic scale. And this is very essential when you tap into very low price iron oxide resources, such as, for instance, the use of so-called banded iron ores, like you see here, which are very high in silicon oxide. So it's a technique that might come in very handy to equip you not only with a very fast and efficient and sustainable reduction technique, but also with a technique that allows you to use very low price iron ores. Here are a couple of process variants shown where we compare the plasma reduction, which is shown here in terms of these stars for different partial pressure, 20% for the yellow ones, again, very, very fast reduction. The green ones with 10% hydrogen with a more moderate but still very fast reduction after 15 minutes compared to direct reduction. The symbol DR here stands for direct reduction, classical solid state type of matrix reactors, also for different operation functions. And you can very nicely see that these curves are much more sluggish. And here particularly the maximum in the reduction kinetics occurs for about 20% hydrogen. And so that shows again that the transformation rates are extremely, extremely fast. What we can also do and what we explored also is a combination of the two techniques where you bring the direct reduction technique where you reduce the material in the solid state and produce iron sponge that you later melt and bring in a liquid form, as you see here on the left-hand side, combined with the plasma method that we have just explained, where you take instead this technique and bring it first into the liquid state and then reduce it in the liquid state, and we do that much faster. But we studied also hybrid or crossover methods, where we say we can combine the efficiencies of the two processes, of the two reactor techniques, by saying let's do the first step in large reactors to do direct reduction, as you see on the left-hand side, typically in a Midrix furnace, and then stop the reduction in between, particularly in the solid state, the wüstheit state, where the reduction becomes very sluggish, very slow, and stop this partially reduced iron sponge, which consists of wüstheit and iron, and charge this, for instance, into a plasma furnace to do the final reduction very efficiently and with a very high electrification degree. So that is a crossover technique that again shows you can combine different sustainable reduction strategies. And that is very important because you see here a comparison between elements like nickel, cobalt, chromium, manganese, and iron, where we typically are concerned with iron because it is a huge quantity of 1.85 billion tons that we produce every year around the globe, but the actual CO2 emission per ton of iron is only about 1.9 to 2 tons per ton of iron. While when you look into these more critical and strategic elements like nickel or cobalt that you need for stainless steels, for special high temperature alloys, for super alloys, or for cathodes for car batteries, for electrical vehicles, and so on, they come in part with a much higher CO2 footprint compared to these standard commodity metals. And also here, we looked into the efficiency of using plasma states for reduction. The reason is quite simple. In iron, we particularly have very high cleanliness ores. That means when you use commercial hematite to charge into such a plasma reactor, you often deal with an iron content in that oxide of 70%. When you take today a typical laterite ore, a weathering ore which contains nickel or cobalt, you often deal with 1.2 to 1.3% nickel only in these minerals. And that makes the processing of these substances and the extraction of the metal so very expensive. And we applied the same technique, also the same plasma smelting reduction technique also to such materials. And you see it for the example of nickel, where we were able with the same type of plasma reduction technique with about 10% plasma to produce nickel directly out of its oxides. And that can be applied to many other techniques, many other metals also. Here we tried it on a different case by using deep sea nodules, so from deep sea mining, which are rich in nickel, cobalt, manganese, copper, and so on. And again, we're able to extract corresponding precursor metals and precursor alloys directly through the hydrogen-based plasma technique. And that is much more efficient again than the land-based mineral production or preparation, drying, kiln operation, and the classical EAF type of operation for metal extraction. So again, the plasma state shown here for the production of nickel and corresponding precursor mixtures containing also manganese and copper and cobalt out of these deep sea nodules. So this is also a very efficient process for different type of feedstocks. At the end, I share a few slides that we can also use the plasma-based hydrogen sustainable reduction for a more circular economy, where we do not use primary minerals from ores, but we use industry waste products. The idea is that when we use dumped and expensive waste, for which you in part have to pay 300 to 400 euros per ton, when you use these to extract the remaining minerals and elements in this material, you have a very interesting business model. And again, we try to do this in a very sustainable fashion and energy efficient way by using hydrogen-based plasma. We used as a demonstrator example here the red mud reduction. Red mud is a very important industry residual from refining bauxite, which is the main mineral used for aluminum production, into pure aluminum oxide, because the mineral bauxite, which is the starting point, contains only about 1/3 of aluminum oxide. The rest are other oxides, and primarily iron oxide, silicon oxide, and sometimes also titanium oxide. And this has amassed to more than 4 billion tons around the globe as a very toxic waste product. Here's a picture that shows how large some of these ponds are. Here you can see you could even, sink the pyramids of Gizeh, the Golden Gate Bridge, or the Wembley Stadium in these ponds, just to give you a feeling how gigantic these red mud residues are. And we run the same operation as I showed to you before. That means we expose this toxic industry red mud, which is iron containing, to this hydrogen containing plasma, often with only about 10%, as I mentioned before. Do the same type of operation that we discussed before, and then you are also able to extract the metal from this toxic industry waste. And here again you see this happens in a very fast pace, as I've shown you before. That means you extract the 30% iron that this red mud typically contains after 10 or 15 minutes, practically completely. And by that, eliminate a very toxic industry waste and extract the valuables from it. The type of intermediate steps are in these red mud substances, owing to the high mineral content, very complicated. I give you here a few glimpses. The details can be found in this publication, but you can appreciate that many intermediate precursor oxide states appear until you finally arrive at the actual extraction of the metal that you want. And again, the actual monitoring and analysis of the reduction that takes place at the acting interface between that plasma and the slag and the ionic liquid is very complex and still subject to further research, just to nucleate some appetite on your side if you find this topic interesting. Last but not least, we also look into the recycling of hard magnets that contain heavy rare earth metals, like for instance neodymium or dysprosium and terbium and so on. And there are nowadays, of course, used magnets on the market, in part highly contaminated. Others are more clean when they come in big chunks. And also swarf that comes from the production of these materials and from grinding operations, from machining operations. And we have a project going on where we subject these materials to the same type of operations, and this will be the subject of further presentations that we can give in the future. This is ongoing work just to stimulate again some interest in these types of plasma operations. So with that, I close this presentation and again summarize or recap here a little bit that we can, with a 10% or less hydrogen containing plasma, reduce all kinds of liquid minerals and even industry waste products and extract from them metal in a very efficient manner after often less than 10 or 15 minutes. And the process also, as we even have shown down to the atomic scale, also cleans up the material and allows you to extract pure metals, as we have shown across the different scales. And again, the details can be found in this paper. And with that, I stop here and thank you very much for your kind interest in hydrogen-based plasma reduction from ores and from industry waste.